I'm very honored to be here to present the new research on behalf of my research group. And the topic here is web service queues prediction based on adaptive dynamic programming using fluid neural networks for cloud services. And my presentation is mainly about three questions. Okay, the first question is, what is the queues prediction in cloud service? And the second is, how do we predict queues using ADP? And the third is the approach we present effective? Then we come to the conclusion. So let's start with the first question. What's the queues prediction in cloud services? The quality of service, also known as QoS, is a non-functional performance of web services, including price, popularity, response time, and failure probability, and many other indices. And response time here is the most important factor or the property to evaluate because users can feel directly of the response time. And so here we discuss the prediction method for response time in queues. And here is a typical cloud service scheme. And we can easily discover in our daily life and in the cloud there are many numerous available services, but actually the users usually do not access to all of them, and there are many similar services in the cloud. So it's become very important to evaluate the quality of the services in order to help the users choose the best services. And the predict queues value has been widely used in different fields, just like service ranking, service composition, and many others. And so the queues prediction method becomes very important. To conduct our performance, our environment, we found a data set which includes the actual queues data of 5,825 real-world web services from 73 countries, and whose queues value was observed by 339 users all over the world. And there are a lot of existing queues prediction approaches. So here we list four of the traditional approaches of queues prediction, and lately we will compare those approaches with the proposed one. So the four traditional approaches we present here is UPCC. This one is to predict the missing queues data based on the collected information from similar users. And the second is IPCC. This one is to predict the missing queues data from the information from similar service items. And the second is UIPCC. This one combines the first one and second one. And the last is the average. The average is arithmetic average value method. And the function is defined as follows. So we come to the next question, the second one. How do we predict queues using ADP? Now here is user component matrix, and it's an example of queues data. And the real queues data is similar to the example we present. And so the problem now is how to precisely predict the missing blank, the blank entries according to the existing entries. So that's what we do with this approach. And we propose the approach considering the nonlinear and the dynamic property of queues data, and as well as the lack of queues data for calculation in some cases. And meanwhile, we also use the fuzzy logic to express the inner relationship of the QoS data. Within the proposed scheme, the fuzzy neural network is implied to approximate the castigo function and the action network in ATP. Then our approach that's the composition of our approach. The first thing is the adaptive network-based fuzzy inference system, also known as ANFRS. This system includes a set of fuzzy if-then rules automatically and optimize the rules within self-learning of a neural network. And compared with the BP network, this system has stronger self-learning ability, robustness, and adaptability, while it can approximate any non-linear function. And this is the architecture of the ANFRS. And the construction of this system consists of 5 layers. The first layer is the fusification layer, and this layer defines the membership function of the nodes, and the function is at the first equation on this page, and it's a Gaussian function, and the rho j on the top of the page is the fuzzy rho of each node, and the second layer is the rho layer. The rho layer, in the rho layer, each node multiplies those inputs and generates the outputs with the function just as equation 2, and the outputs of this layer stand for the firing strength of the rule. And the second layer is the normalization layer. In this layer, the nodes generates the weights according to the third question, the third equation, And the fourth layer is the diffusification layer. And nodes in this layer are calculated by the fourth equation, and the last equation is upper layer. The nodes calculates the sum of the outputs from the fourth layer, and according to the equation 5, and this system integrates the BP algorithm and the least square estimation algorithm. It has a very fast, rapid learning speed, and in the training process, the parameters of if-then rule can be identified by LSE in the forward pass, and in the backward pass, the error rates propagate backward, and the expressions and variances of Gaussian function are updated by the BP algorithm. Then we come to the next part, the adaptive dynamic programming. So this is ADP is an optimization technique which combines conceptions of reinforcement learning, such as Q-learning, and dynamic programming. It can estimate the castigo function within the use of the neural networks, and the neural network is as a function approximator, and there have been different structures coming up since the ADP was proposed. So in our approach, our approach is based on the HDP structure. And the HTTP structure is to estimate the castigo function in the Bellman equation of dynamic programming. And the web services QoS response time dataset is summarized as follows. The scale of response time is from 0 to 20 seconds, and the mean of response time is 0.91 second. And the number of users, just as mentioned before, 339. The number of web services is 5,825. And we also calculate the MAE and MAP to compare the prediction quality of our approach, and also compared with other methods. And MAE and MAP are defined as follows. It's a mean absolute error and mean absolute percentage error, respectively. And here is a performance comparison table. The metric density stands for the percentage of the data from the dataset are removed from the dataset, and our prediction is based on those metrics density. So we calculate the MAE and MAPE, and we do the experiments with those approaches, also our proposed approach. And these two diagrams show the curve of prediction MAE and the prediction MAPE respectively, and the green curve stands for the experimental results of the proposed approach. And we can see from the diagram that a proposed approach has better prediction performance than the rest approaches, and more stable and more accurate. Then this diagram shows experimental results with the 70% metric density. This is the curve. This is the tracking curve of different approaches, and also the green one stands for the approach we proposed, and the red curve is the actual data. So we can see from this diagram, our proposed approach tracks the actual data the best, better than the rest of the approaches. So we come to the conclusion part. So in conclusion, we propose a new approach, a QoS prediction scheme, and through the fusion of FNN, the fusion neural network, and adaptive dynamic programming, and also we compare those traditional methods with our proposed methods, and also shows the better performance, the advantage of our proposed method over the traditional method. And in the future, a test of this approach on bigger data sets will be conducted and analyzed. Thank you. Thank you for listening.